Okay, so today I'm going to solve this problem on from Putnam 2019 B2. And the question is essentially asking you to find a limit. Although the limit involves a series. Um, so the first thing I see when I see a sequence, and in this case, it's basically a sequence of partial sums, which is, it's kind of basically asking you to estimate the infinite series. In other words, it's saying that um, if you compare that sum with n cubed, how large is that sum with respect to n cubed? So one way of thinking about this problem is to try to find that sum and then divide by n cubed and then take the limit. On first glance, that might seem a bit of a difficult task because finding that sum may not be as easy as we might initially think. And also, they didn't require us to find the sum. We really just need to find an approximation for that sum. But it is certainly worth trying and seeing if we can actually find that sum. So that's certainly one approach. So when we want to find sums, we usually have different options. Either your sum is one of the known sums, like a geometric sum, or sums like sum of 1 over n squared or sum of 1 over n and things like that, that you can test whether they're convergent or divergent, or you can find them using formulas that we have. Or it is one of those power series. If it is, it can be related to a power series of sine, a power series of cosine, or perhaps e to the power of x. Those could be those are some certain types of sums that you can evaluate. And the last option is usually trying to write down a sum as a telescoping sum. So first, let me kind of quickly tell you what a telescoping sum is. So if you can write down your sum as the sum of bn minus bn minus 1, n goes from 1 to some k, it means you have b1 minus b0 plus b2 minus b1 plus bk minus bk minus 1. So if you take the difference of these, basically all of the terms are going to cancel except for the last term and the first term. So you get bk minus b0. So that kind of sum is called a telescoping sum. Okay, so those are like basically my three possibilities. Either finding the sum in terms of one of the famous sums, or relating that to a power series, or using the technique of a telescoping sum. Those are three different ways of finding a sum. If you want to find limits of sums, it's also potentially possible to relate it to an integral. So if you have an integral, let's say from 0 to 1 of f of x dx, if your function is integrable, then you can write it down as the limit as n goes to infinity of 1 over n times, so basically Riemann sums, times f of 0 plus f of 1 over n and so on. So that's a Riemann sum, and you can find the limit of you can find some limits of this form using integration. Okay, so these are like essentially different ways of approaching problems like this. Let's see if we can do a telescoping sum. So I see that in the denominator, I have two terms, cosine squared of k minus 1 over 2n times pi, and cosine squared of k pi over 2n. So the nice thing about these two terms is that they're actually quite similar, meaning that if I replace k by k plus 1 in the first term, I get the second term. So that does remind me, or I guess reiterate, the similar thing that we just saw here. So as you see here, you have bn and bn minus 1. So you have two terms that they are basically the same sequences, it's just shifted. So if I can somehow write down this fraction in a similar fashion, then I would be able to solve the problem, hopefully. Okay, so that's my first approach. Let's see if that works. So the fraction was cosine squared of k minus 1 over 2n pi, cosine squared of k over 2n pi. Okay, so my goal is to write it down as something over cosine squared of k minus 1 over 2n pi. So let's call that a, to be determined. Something over cosine squared of k over 2n pi. And hopefully, if I can find a and b, and they are of the similar format, then I can do a lot of cancellations. I get a telescoping sum, and then I can solve the problem. It's not clear whether I can do that at this point or not, but that's certainly worth trying. So let's clear the denominators and see what we get. So we get sine of 2k minus 1 over 2n pi equals a cosine squared of k minus 1 over 2n pi plus b, sorry, this should be k, b cosine squared of k minus 1 over 2n pi. So if I can find a and b that satisfy this, then I would be done. So what I'm going to do is I'm going to use some trig identities. That seems like a reasonable thing to do. So I'm going to reduce the exponent to just get something a bit more linear for both of these two. So I have this identity, 2 cosine squared of alpha is 1 plus cosine of 2 alpha. So I have this identity. So I'm going to use that. So I'm going to multiply both sides by 2. So I get 2 sine of 2k minus 1 over 2n pi equals a. 2 cosine squared is 1 plus cosine of double angle, k over n pi. And then 1 plus cosine of, again, double of that angle, so k minus 1 over n times pi. Okay, which is, if I combine the constants, I get that, and then the rest of that becomes a cosine of k over n pi plus b cosine of k minus 1 over n pi. Okay. So it is still not clear what a and b would be useful, or whether even there exists an a and b or not. So here's what we're going to do. We're going to hope that we can come up with a and b that this equality holds for them. And it makes sense that maybe this should be 0 and this should be equal to that. Let's see if that works. So can we choose a and b such that a plus b is 0 and 2 sine of 2k minus 1 over 2n pi is a cosine of k pi over n plus b cosine of k minus 1 over n pi. So is it possible to choose a and b that satisfy this? Okay, maybe yes, maybe not, but we'll see. So this gives you b equals negative a. And if you plug it into the bottom one, you get 2 sine of k minus 1 over 2n pi equals, so b is negative a, so you can factor in a. You get cosine of k pi over n minus cosine of k minus 1 pi over n, which is, okay. So this one can be written, I'm going to turn that into a product. So I'm doing the sum to product, difference to product. So the identity that I'm using is cosine of alpha minus cosine of beta is 2. So when you subtract 2 cosines, you get twice product of sines. So it's beta minus alpha over 2 sine of the average. Okay, so that's what we get. So it is a times 2 sine of the difference over 2. So that is minus pi over 2n, and then sine of the sum over 2, 2k minus 1 over 2n pi. So that is really perfect because this exactly cancels with that. So I get what a is. I get a is equal to, and the 2 also cancels. So I get the exact value of a in a way that should help me solve the problem. So minus pi over 2. Okay, so this is very hopeful. This makes me think that I should be able to solve the problem. So the initial fraction that I wrote, which was over cosine squared k minus 1 over n pi times cosine squared k over n pi, is in fact equal to, so it's cosine squared of k minus 1 over n pi minus or plus, I guess the a is negative 1 over sine of pi over 2n, and then plus b was negative of that, so 1 over sine of pi over 2n over cosine squared of k over n pi. So this is what we get. If we take the sum, this was our, I guess, this wasn't the an, this was just one of the terms of an. So an is the sum of all of these. K equals 1 to n minus 1. Let's go back and take a look at what an is. An is that. So I'll have to take the sum of those. So fortunately, all of those are independent of, all of the numerators are independent of k. So it's 1 over, so I'll take that out. I get 1 over sine of pi over 2n times 1 over cosine squared of k pi over n over 2n, I believe. I believe it was 2n. Yeah. Okay. So I guess I get this over 2n minus 1 over cosine squared of k minus 1 over 2n times pi, and that's it. So that's the sum. Now, clearly I can factor 1 over sine of pi over 2n. And what I get from the rest is 1 over, so cosine squared of pi over 2n, if you substitute k equals 1, you get that. Minus, well, actually, no, you have to substitute k equals n minus 1. So we get that. And from the other one, we get sine of cosine of 0. So we get 1 over n minus 1 over 2n times pi. If you substitute k equals n minus 1 minus 1 over cosine squared of 0 if you substitute k equals 1. Which gives you 1 over sine of pi over 2n times cosine squared of n minus 1 over 2n pi. And then we get 1 minus cosine squared of n minus 1 over 2n pi. Okay, so the numerator becomes 1 over sine of pi over 2n. The numerator becomes sine squared of n minus 1 over 2n pi. And the denominator is cosine squared of n minus 1 over 2n pi. Okay. So this may be easier to turn into, if you simplify that, this angle is going to be pi over 2 minus pi over 2n. And sine of pi over 2 minus an angle is cosine. So it's cosine squared of pi over 2n divided by sine of pi over 2n. And this one is also sine. So sine squared of pi over 2n. So it becomes cosine squared of pi over 2n over sine cubed. Okay, so now as n goes to infinity, the limit as n goes to infinity of an over n cubed becomes the limit as n goes to infinity cosine squared of pi over 2n divided by sine cubed. This is your an, and then you have to multiply that by n cubed. Now, as n goes to infinity, this angle goes to 0, which means its cosine goes to 1. And this angle goes to 0 also, which means we'll have pi over 2n cubed over sine cubed of pi over 2n. This would approach 1, and then you have to multiply it by, to cancel that, you have to multiply it by 8 over pi cubed. So the final answer becomes then 8 over pi cubed. Okay, so this is how you get the solution. But I do also want to go over how to write down the solution. Okay, so I guess I'm gonna write down my final answer here. So we will prove limit of an over n cubed is equal to 8 over pi cubed as n goes to infinity. So that's the first thing I'm gonna do. Just write down exactly what I'm going to prove. Instead of doing all of this and finding this telescoping sum, I'm gonna write down the claim that the sum is whatever I claim it to be. And then I'll prove that by induction. That is gonna help me simplify things. So we will prove that in fact the sum is this sum right here. So we'll prove this. And yeah, so I'm gonna write this down. So claim is an equals 1 over sine of 2 pi n times, so I have it right here, 1 over cosine squared n minus 1 over 2n well, actually, you know what? I can't really prove that by induction because I have to change n. So I'm going to, yeah, okay, yeah. So I'm gonna just write it down here. Yeah, I was thinking of using induction, but no, that may not be a good idea. Okay, so I'm gonna write down this claim, and then I'll prove that by checking the each of these is equal to that. So I'll just show that. Okay. So note that. Okay, so we will prove the term that I had, which was sine of 2k minus 1 over 2n pi over cosine squared of k minus 1 over 2n pi cosine squared of k over 2n pi is equal to 1 over sine of 2 pi over n times, so 1 over sine of 2 pi over n times 1 over cosine squared of k minus 1 over 2n pi So let me go back and take a look, or I guess it was the k was first. So that minus the other one, minus 1 over cosine of k minus 1 over 2n pi. Okay, so we will prove this one. And you could do that. So this is equivalent to showing sine of 2k minus 1 over 2n pi is equal to 1 over sine of 2 pi n times, if you just clear the denominators, you get cosine squared of k minus 1 over 2n pi minus cosine squared of k over 2n pi. So we get that, which is equivalent to, so 2, I'll clear the denominator and then I'll multiply everything, both sides by 2. 2 sine of 2k minus 1 over 2n pi sine of 2 pi over n equals 2 cosine squared of k minus 1 over 2n pi minus 2 cosine squared of k over 2n pi. And then by double angle formula, the right hand side is equal to, so if you look at the right hand side, 2 cosine squared is cosine of double angle. So cosine of k minus 1 over n pi minus cosine of k over n pi, which is the same as, and then you could just evaluate that by the sum to product or difference to product formulas. So it's 2 sine of pi over 2n times sine of 2k minus 1 over 2n pi. Since cosine of alpha minus cosine of beta is 2 sine of beta minus alpha over 2 sine of beta plus alpha over 2. Okay, so we proved this claim that I had here. We proved this claim, this one here. So therefore, an becomes 1 over sine of 2 pi over n times the sum k equals 1 to n minus 1, 1 over cosine of k pi over n, cosine, I guess, squared of, let me see what we have here, cosine squared of k pi over 2n. This pi should be inside the angle. So, okay, so k pi over 2n minus 1 over cosine squared of k minus 1 over 2n pi, which is equal to 1 over sine of 2 pi over n times, so you plug in k equals n minus 1, you get 1 over cosine squared of n minus 1 over 2n pi. You plug in k equals 1, you get 1 over cosine of 0, which is equal to 1 over sine of 2 pi n. And that's just, the numerator becomes 1 minus cosine squared, which is sine squared of n minus 1 over 2n pi over cosine squared of n minus 1 over 2n pi. So since n minus 1 over 2n pi is pi over 2 minus pi over 2n, we get that an becomes 1 over sine of 2 pi over n, or was it pi over 2n? I think I missed it as, yeah, it was pi over 2n. Yeah. So pi over 2n becomes, yeah, this is all pi over 2n rather than 2 pi over n. So that becomes pi over 2n times, I have cosine squared of pi over 2n, and then sine squared of pi over 2n, which is going to be cosine squared of pi over 2n over sine cubed of pi over 2n. Now, we will see that the limit as n goes to infinity of sine of pi over 2n over pi over 2n is in fact 1. Thus, limit of sine cubed of pi over 2n over pi over 2n cubed is 1 as n approaches infinity. So that means if I take that sine of pi over 2n and cube that and multiply by n cubed as n goes to infinity, you're going to get pi over 8, pi cubed over 8. Okay, so that means the denominator times n cubed is going to be pi cubed over n, pi cubed over 8. So that means this is equal to limit as n goes to infinity, cosine of pi over 2n, that's just cosine of 0, divided by n cubed sine cubed of pi over 2n. Numerator is 1, denominator is pi cubed over 8, so that becomes 8 over pi cubed, which is exactly what we claimed to begin with. So that 8 over pi cubed is what I claimed from the beginning. So that completes the proof.